Hello, welcome. In this video we are going to discuss an important property of Legendre symbol, and after that we will discuss an application of this property. See, that property is that whenever the two numbers m and n are congruent with each other, that is if m is congruent to n mod p, if the two numbers are m and n, and if they are congruent with each other, then the Legendre symbol, corresponding Legendre symbols, that is m bar p, n bar p, these values are also equal. In other words, if m bar p equal to n bar p, then m is congruent to n mod p, and also if m is congruent to n mod p, we can say that if m is congruent to n mod p, then m bar p equal to n bar p. So this is the summary of that property, and that property can be then related to will tell us that it tells us that the function, the Legendre symbol, that function is periodic. That particular function, the Legendre symbol, is periodic. It is then periodic with the period p. We know that the Legendre symbol can take only three values: 0, +1, or -1. Depending upon whether n is so see, we are talking about n bar p, the Legendre symbol n bar p. So if n is a multiple of p, then we have n bar p equal to 0. If n is quadratic residue mod p, then we have n bar p equal to +1. Otherwise we have -1. That is, if n is not quadratic residue mod p, quadratic non-residue mod p, then n bar p equal to -1. So as in the application, you can then add to the number. Suppose, assuming that n bar p equal to n is the number we are taking, and n bar p equal to k, then we know, as we have discussed, k can take any one of the values, 0, +1, or -1. So you can add any multiple of p to the given number n, and then you can see that n plus p, for example, n plus p bar p equal to k. The Legendre symbol n plus p bar p equal to k, the same number. Generalizing this, you can say that n plus m times p, n plus m times p, m times p is the mth multiple of p, that is added to n, and when we take the Legendre symbol value with respect to p, we get the value equal to k, the same value. So when we apply, you can apply it in some examples. We know that 7 and 8 are quadratic non-residue mod p. So 7 bar 11 equal to -1, 8 bar 11 equal to -1. Therefore 7 plus 11 bar 11 will also be, that is 18 bar 11 equal to -1, and 8 plus 11 bar 11, that is 19 bar 11 will also will be -1. And 29 plus 11, 29 equal to 22 plus 7. So you can separate 22 from this number and get that 7 here, and get 7 here, and 7 plus 11, and that will be becoming equal to this number, this quantity, and that will be equal to -1. So this is the application. Then what does these steps say? It says that we can apply that periodicity of Legendre symbol to obtain the Legendre symbol value for a very large number of numbers without taking much effort. We can easily find the values. Now we are coming to the Fermat's theorem. Little Fermat's theorem, that says that n raised to p minus n is congruent to 1 mod p. Importance of discussing this theorem here is we have some applications of this theorem in the following section, the next sections. Okay, that theorem says that n raised to p minus n is congruent to 1 mod p, and when we transfer 1 to the left side, we get n raised to p minus 1 minus 1 is congruent to 0 mod p. But you can write then this quantity equal to n raised to p minus 1 by 2 the whole square, and you can see here when by writing the note here, one that term was missing. That I forgot to write that term. That is -1 here. So actually -1 is here. It's a mistake. So, and here to obtain this step, we considering you should know that there is a mistake, that -1 is missing, so you have to put -1, and then we here first term is n raised to p minus 1, that can be written n raised to p minus 1 divided by 2 the whole square, and minus 1, that 1 can be written 1 square. Okay, then we have a square, this expression, the left hand side expression of the congruence, as a square minus b square, in the form a square minus b square. You can write that you can split it into into two factors, and you can get a minus 1 into a plus 1, right? A minus 1 into a plus 1 is then congruent to 0 mod b. A minus 1 into a plus 1 is congruent to 0 mod p. Then that a minus 1 part will be n raised to p minus 1 by 2 minus 1 is congruent to 0 mod p, and n raised to a plus 1 part is n raised to p minus 1 by 2 plus 1 is congruent to 0 mod p. Okay, and therefore this is, this happens either that either of the two statements is correct, not both. There is no guarantee that both statements are correct, but but one of the statements must be correct in this case. Therefore we have n raised to p minus 1, then when we transfer that plus 1 or minus 1 to the right side of the congruence, we get that n raised to p minus 1 by 2 is congruent to 1 mod p, or n raised to p minus 1 by 2 is congruent to minus 1 mod p from the second statement. Okay, and this is then you get that okay, and this is explained here, and again it is explained here in its original form. It's explained here. So, or we have that statements, first statement or the second statement, and then we get this statement or this statement true. And thus you can combine these two, since these are either first or the second type of statement. You can combine that. You can write it as a single expression. Then we get that n raised to p minus 1 by 2 is congruent to plus or minus 1 mod p. So we get n raised to p minus 1 by 2 is congruent to plus or minus 1 mod p. That is the consequence of that discussion. Thus, in the next theorem, we shall show that n raised to p minus 1 by 2 is congruent to 1 mod p if n is quadratic residue mod p, and n raised to p minus 1 by 2 is congruent to minus 1 mod p if n is quadratic non-residue mod p. And that's the importance of this small discussion on Little Fermat's theorem. What we are going to do in the next theorem? In the next theorem, we are going to show that n raised to p minus 1 by 2, that is theorem 9.2, n raised to p minus 1 by 2 is congruent to 1 if 1 mod p if n is residue nrp, and if n is quadratic residue mod p, and it is congruent to n raised to p minus 1 by 2 is congruent to minus 1 mod p if n is quadratic non-residue mod p. A quadratic non-residue mod p is usually written n r prime r bar over this line over r p, and this is the way we write it. Symbolically we write it, n is quadratic non-residue mod p. So coming to the theorem, we have different cases to discuss to complete the theorem. We have to discuss many cases, so and that will be discussed in a separate video. Okay, right? Then okay, else we are going to end this video. Thank you.